Welcome to One Chemistry. We are seeing organic chemistry concepts. In this video, we are going to see regioselectivity. We will learn the basics and we will analyze it very detailedly by 86 examples. Stay tuned. What is inside this video? First, we will see what is regioselectivity. Then we compare regioselectivity with chemoselectivity. Then we are going to see types of regioselectivity, basically 5 types, and common reaction with regioselectivity. Finally, we are going to see 86 fully solved examples from various exams. It will help you to understand the concepts better. First, let us see what is regioselectivity, what is the basics of it, what is the mechanism behind that. Here toluene, if you see, here NO2 can form ortho, meta or para. You should find where the NO2 form because all are carbon, only differ in the region. That's why it is called regioselectivity. Then you should know difference between regioselectivity and chemoselectivity. Regioselectivity means which region will be attacked because all are carbons. On the contrary, chemoselectivity means which functional group will be attacked. Here you have alcohol and aldehyde. In chemoselectivity, you should find whether alcohol or aldehyde reacts. So you should know basically the difference between regioselectivity and chemoselectivity. What are all the regioselectivity types? You can promote the regioselectivity by the choice of the reactant or by the choice of the reagent, or regioselectivity can be promoted by cation, anion or aromaticity stability. Then ring size also can promote regioselectivity and steric effect also one of the factor. So 5 different controlling factors. You should master all the factors. First, let us see reactant control. This is the classic example. You have methyl and nitrobenzene. You are reacting with electrophile. Electrophile in toluene attack ortho and para, not meta. On the contrary, nitro, electrophile attack only meta. All the answer lies in the mechanism, electron density. Toluene, ortho and para positions are denser. In nitro, only meta is electron denser. So electron withdrawing group promote the meta position. Electron donating group promote the ortho and para position. So typical regioselectivity by reagents. So typical regioselectivity by reactant. Then regioselectivity by reagent. Starting metal is dimethylbenzene. You are reacting with two different reagents. One is bromine with light, another is bromine with aluminum chloride. The light promote the radical mechanism. Benzyl radical is stable, so substitution happen at the benzylic position. On the contrary, aluminum you are using mean aluminum chloride is the Lewis acid. It activates the ring. Substitution happen at the ring. So two different reagents, two different products. It is the typical regioselectivity by reagents. Then regioselectivity and stability. Here you are having starting material with diene which contain two diene A and B and one dienophile. You are doing Diels-Alder reaction which is 4 plus 2 cycloaddition. If A diene reacts mean you have benzene ring, B diene reacts mean you have strained full bicyclic compound which is highly unstable because of bond angle. sp2 carbon need 120 degree, here only 90 degree, highly unstable. So the major product formed by B diene. So the concept you have to learn here is stability also can promote the regioselectivity. Here benzene is stable because of aromatic character which promoted regioselectivity. Then regioselectivity versus ring size. Here starting material you are having acid, you are using SOCl2 which is chlorinating reagent. which converts acid into acid chloride. Acid chloride can react many ways because you have the possibility of ortho and para, but reaction happen at only ortho. Why? Because ring size promote the regioselectivity here. Only 6-member ring is stable, not the strainful rings. If you look at the ring strength, 6-member ring is least, 3-member ring is highest. So 6-member ring always form. So the concept he outlined here is regioselectivity can also influenced by the size of the ring in the cyclization reaction. Then regioselectivity versus steric effect. Starting metal is epoxide with 2 methyl group. You are reacting with methoxide. So SN2 reaction is possible. SN2 reaction required backside attack. So nucleophile always look for the less steric position. So if you look at it, less steric position means it is away from the dimethyl group. So major product will be attack on the B pathway. A pathway is steric, B pathway is less steric. So the ring is open on the less hindered pathway. Final product is alcohol. This is the typical example of sterically controlled regioselectivity. Then the regioselectivity with specific reaction. Regioselectivity versus Michael addition. Michael addition is the important factor in the regioselectivity because it is always dictated by the nucleophile. Here conjugated ketone is there. You are attacking with nucleophile. Nucleophile can attack 1,2 position or 1,4 position. Based on the hard and softness, nucleophile attacks. Hard nucleophile mean it will attack 1,2 position. Mostly magnesium and lithium nucleophiles are hard and soft nucleophiles undergo 1,4 addition. Copper and sulfur halides are soft nucleophile. Here we are using methyl magnesium bromide, which is a hard nucleophile which attacks. You have the final 1,2 addition product. So you should master the Michael addition to understand the regioselectivity. Then let us see regioselectivity versus pitch reduction. Pitch reduction is a regioselective reduction. Only 1,4 carbon is reduced. Pitch reduction involves anion as the intermediate. So electron donating and withdrawing group can influence the reaction. Electron donating group destabilize the anion. So the reduction happen at the 2,5 position in terms of electron donating group. In the case of electron withdrawing group, 1,4 reduction happens. So pitch reduction is the regioselective reduction. Electron withdrawing and donating group can influence the final product. So pitch reduction is the important regioselective reduction reaction. Then regioselectivity versus ortholithiation. Ortholithiation is the important concept because you are activating only ortho carbon, that is ortho hydrogen. It is possible by cyclic 6-member intermediate. Lone pair on the substituted atom helps here. Starting middle is amide. There nitrogen has lone pair which can coordinate with lithium, promote the ortho hydrogen. Then it forms final product new CC bond. Here only substitution happen at ortho because of intermediate, because of ortholithiation. It's a regioselective lithiation reaction, very important in terms of regioselectivity. Then regioselectivity versus Benzyne mechanism. Whenever you have halobenzene, Benzyne intermediate is possible. But next step is interesting because nucleophile can attack second or third position. The attack leads to the anion formation. So the possibility of regioselectivity. Anion is the intermediate. It can be stabilized or destabilized. Electron donating group is here. It is destabilized the anion. So anion form away from methyl. You have major product which is meta. Here regioselectivity only at meta, not at ortho or meta or para. So regioselectivity by benzyne formation. So the benzyne mechanism is important for the regioselective reactions. As a part of the understanding, we solved 86 examples. Why we solve so many examples for a single concept? Because problems are best way to learn the concept. So too many problem mean you are understanding the concept in many perspective. So the error will be less. Accuracy in your prediction will be strong. We will see one by one. The first example is very simple and obvious one. Here you have one butene with HBr. You have to find what could be the product. Here you have two nucleophiles where it can attack. Whether A or B attack, you will have final product. But A carbon attack leads to the primary cation, B attack leads to the secondary cation. If you look at the stability, tertiary is more stable, then comes secondary, then primary. So major is B attack, final product is bromine there. This is called Markovnikov rule. You might have studied without knowing. It's a regioselective reaction. So you are choosing between A and B carbon. H plus attack B favorably to achieve the final product. Then you will see the next example. Here you have paramethylanisole with acid chloride and aluminum chloride. You should find what will be the final product. Here you have two electron donating group is there. One is methyl, one is O-methyl, which is methoxide. Where the reaction happen, ortho, meta or para. Here reaction happen at ortho position, which is respective to O-methyl group. Because O-methyl group creates the mesomeric effect, it has lone pair of electron it can promote, which is favorably formed. On the contrary, CH3 is electron donating by hyperconjugation like activity. So O-methyl is a kind of full electron donation. So O-methyl influence the reaction more. Ortho to O-methyl is the major product. Then the next example, you have alkyl bromide with many substitution. You are using alcoholic KOH. You should find what will be the final product. Here you have alcoholic KOH which promote HBr elimination, but you have two hydrogen which is relative to bromine A and B which will be eliminated. By looking at blind side, you may realize both can be possible, but if you look at the alkene stability, most substituted alkene is stable, which is called Sesap rule. So only A elimination gives the major product, minor product will be B elimination. More substituted alkene is stable because of heat of hydrogenation. So major product will be A hydrogen eliminated product. Then the next example. Here you have methylanisole. You are reacting with lithium and liquid ammonia. You should find what will be the final product. The reaction is called bridge reduction. Basically, it's a regioselective reduction. The double bond formation dictated by electron donating ability of the functional groups. If the functional group is electron donating group, double bond form away from it because intermediate is the anion. If it is electron withdrawing group, double bond form. If the functional group is the electron donating group, double bond form near it. If it is the electron withdrawing group, double bond form away from it. Here you have two electron donating group, O-methyl and methyl, but O-methyl is stronger due to the mesomeric effect. Mesomeric effect is full electron donation. Methyl is hyperconjugation type. O-methyl donate full pair of electron, very strong. So the reduction dictated by O-methyl. A is the major product, not the B or C. So the concept you have to learn here is regioselectivity in bridge reduction dictated by electron donating ability of the functional groups. Then the next example, you have cyclohexane quaternary amine in the side chain. You are heating it up. You should find what will be the final product. The quaternary amine comes in heating condition. It's a Hofmann elimination. It's a regioselective elimination of hydrogen. Here amine has to be eliminated with hydrogen. There are two possible hydrogen A and B. Which hydrogen will be eliminated? The hydrogen with less steric effect will be eliminated because the leaving group is the bulky, the approach and elimination will be harder. So what really happened? A hydrogen eliminates, not the B hydrogen. It is opposite to Sesop rule. Less substituted alkene will form. The concept we outlined here is Hoffman elimination is a regioselective elimination. Always less substituted alkene will form. Then the next example, you have linear compound with two ketones inside. You are using basic condition. You should find what will be the final product. If you redraw the compound, you might see the possibility of aldol reaction because many alpha hydrogen is there. So which will remove? Here two sets are there, A and B. But B elimination is feasible because it will form only perfect ring size. So B hydrogen eliminates, you have nucleophile or anion formation. The enolate form, it attacks the carbonyl, ring closure happen. You have 5-member ring. Then finally water elimination. You have the final product. Here what is special? Because the hydrogen elimination is the regioselective step. Even though secondary anion is less stable than primary, it forms because more substituted enolate always will form. So B hydrogen eliminates promote the regioselectivity here. Then the next example, you have dichlorobenzene, you are reacting with aluminum chloride and acid chloride with side chain chlorine. You should find what will be the final product. The reaction is very interesting because starting metal has many possibilities, regioselectivity and chemoselectivity. First, let us eliminate the chemoselectivity. Chemoselectivity is not possible because cation formed by chlorine removal is unstable, which is B chlorine. So only A chlorine removal is possible. If A chlorine remove also, you have acyl cation. Where the acyl cation comes, that is called regioselectivity here, where it will attack ortho, meta, para or ortho to which chlorine. Here three types of products are possible, PQR. P product is a very steric product because it's formed between X and Y chlorine. Approach is hard, so it is a minor. Then if you look at the Q, Q is meta to both the chlorine. Chlorine is basically mesomeric effect promoter, ortho para director, so it is not possible. So only possibilities are it will attack the para position to X, ortho position to Y. So it obey all the possibility. So R is the major product. The concept we outlined here is regioselectivity can be promoted by many factors. Here it is steric effect. Then the next example, you have cyclohexenone. It's a conjugated ketone. You are reacting with methyl magnesium bromide. You should find what will be the final product. Here the reaction is basically a regioselective addition. It's a very regioselective reaction promoted by the nucleophile. Normally, two types of nucleophiles are possible, hard and soft nucleophile. Hard nucleophile promote 1,2 addition, soft nucleophile promote 1,4 addition. 1,4 addition also called Michael addition. Here methyl magnesium bromide is there. It will only give hard nucleophile CH3 minus. CH3 minus always attack the second position. So 1,2 addition happen. Alcohol forms, methyl attacks 1,2 position. So it is called 1,2 addition. The concept we outlined here is regioselectivity promoted by the reagent here. Final product is 1,2 addition. Then the next example, you have naphthalene here connected through dimethylene. You are reacting with N-bromosuccinimide light and carbon tetrachloride. You should find what will be the final product. Here NBS and light condition, bromination is possible, but where the bromination is possible, that is the regioselective question here. Bromine can attack ring, both positions are possible. Here I given all possibility, P, Q, R, S. Let us analyze one by one. P is minor because ring substitution needs Lewis acid, so it is not at all possible. The Q is major because side chain substitution as well as benzyl radical stability is possible. That is the major one. So minor and major. Then second NBS where it will attack. It can attack vicinal or geminal. Vicinal means nearby carbon, geminal means same carbon. Here, bromine is the bulkier one. Same carbon attack is not possible. So it attacks the nearby carbon. So vicinal bromine is formed. It is the major product. The concept we outline here is first regioselectivity promoted by the reagent, second regioselectivity promoted by the steric effect. So two regioselectivity. Then the next example, you have cyclohexanol. Second position, you have side chain, which is the ketone with side ethyl group. You are reacting with base. You should find what will be the final product. If you redraw the molecule, you might realize the possibility of aldol condensation. Intra-aldol condensation is possible. There are three sets of hydrogen A, B, C. That is the regioselective possibility, which hydrogen will be removed. Only the C hydrogen removal leads to the feasible reaction because it can promote the ring formation with less ring strain. A removal will be useless because it will undergo intra-aldol condensation, which is less effective than intra. If you remove the B, ring size will be less, so it is not at all possible. So only possibility is C there. C attacks, ring closes. If you redraw nicely, you have new 6-member ring. Finally, water removal, final product. The concept you outline here is regioselectivity promoted by the ring size. The 6-member ring size is more stable by using the Bayer-Stein theory. So the regioselectivity promoted by the ring size. Then the next example, you have benzene and conjugated acid, which is alpha, beta and saturated acid. You are reacting with aluminum chloride. You should find what will be the final product. Here the question may arise, alkylation or arylation will form because you are using the acid chloride. Acid chloride can encourage alkylation or acylation. Let us analyze the stability of the cation. First step, cation will be on oxygen, which is highly unstable due to electronegative nature. Second one, cation near the double bond, which can be switched up, which can be resonance stabilized. So cation moves, only alkylation is possible. So cation stability promote the cation at the terminal carbon, which is tertiary carbon, which attacks the benzene ring. Fiddle crafts alkylation happen. So the cation stability promote the regioselectivity. Then the next example, you have cyclohexane methyl isopropyl chloride attached to it. You are using the base sodium methoxide. You should find what will be the final product. The question is all about regioselectivity. You are using the base. Base remove the hydrogen and halogen. The two possibilities here, if you redraw nicely with hydrogen, you have two possible hydrogen A and B. Both removal leads to the alkene, but only one alkene is there, alkene P and Q. Only Q is major because of the more substitution. In alkene, more substituted product is stable. It obeys the Sesov rule. So more substituted alkene form which promote regioselectivity. The concept we outline here is alkene stability can influence the regioselectivity. Always most substituted alkene with form with chlorine. Then the next example, you have benzene and cyclohexanol. Methoxy group is there. Lithium and liquid ammonia you are using. You should find what will be the final product. By looking at the reagent and reactant, you might realize it's a bitch reduction. But where the reduction happen is the regioselective factor here, where the ring will reduce. Normally, diradical form in this situation, but where the diradical stable, which confirms the regioselectivity, diradical cannot form near the O-methyl group because of the repulsion. Same charges repel each other, and another possibility don't have any extra stability. So anion can form only near electron withdrawing carbonyl. So carbonyl group stabilize the anion. the reduction happen, you have the final product. Simply you can say carbonyl is electron withdrawing, double bond form away from it. The concept you outlined here is regioselectivity promoted by the anion stability. Carbonyl stabilize the anion which promote the regioselectivity. Then the next example, you have decline with one ketone, one conjugated ketone. You are using sodium borohydride. You should find what will be the final product. Here you have two ketone. You are using sodium borohydride. Sodium borohydride is a weak reducing agent which carbonyl reduces the regioselectivity A or B. The possibility are PQRS. P is the major product. Why? Because P carbon has higher electron density. Boron is the electron withdrawing group. It's a Lewis acid. It always takes electron dense carbon. So A carbonyl reduce. So P is the major product. Q is not the major product because alkene is reduced. Additionally, alkene is in conjugation and delocalization. It's less electron denser. And R is also less electron denser. And R is also same condition. The carbonyl double bond in delocalization, which is also less electron denser. S is all reduced. It is not at all possible. So major product is A carbonyl reduced product. The concept you outlined here is even the reducing agent can participate in the regioselectivity. Here sodium borohydride attacks the electron denser carbon. Then the next example, you have para-hydroxyanisole reacting with sodium hydroxide and epoxide with side chain chloride. You should find what will be the final product. Here you have two regioselectivity. You can call it as chemoselectivity also because it's a two functional group. You have two nucleophiles because O-methyl is nucleophile by lone pair and alcohol is also having negative charge which will attack. Here alcohol has negative charge there, so it is very unstable and very reactive, so it will only participate. And again three possibility how the ring will open, A way or B pathway or C pathway. Here A pathway and B pathway are very steric, so only C is possible. So how the ring open? C breaks, oxygen attacks the C carbon, it opens, you have final product. Then O minus attacks, you have epoxide again. The concept you outlined here is epoxide ring opening is a regioselective ring opening. Steric effect promote the regioselectivity here. The concept you outlined here is steric effect can also promote the regioselectivity. Then the next example, you have cyclohexenone, it's a conjugated ketone. Third position you have O-methyl group. You're reacting with phenyl magnesium bromide. It's a Grignard reagent. In acidic condition, you should find what will be the final product. Here regioselectivity is there because you have hard and soft nucleophile condition. Here phenyl magnesium bromide provide the hard nucleophile, so it will add in 2, so it promote 1,2 addition. Hard nucleophile promote 1,2 addition, so 1,2 addition happen, you have phenyl and alcohol. Then you have O-methyl group. O-methyl also can be acidified, form as the ketone here. So the concept you outlined here is you have to analyze. Nucleophile also can promote the regioselectivity. You have to analyze whether the nucleophile is hard or soft. Soft nucleophile promote 1,4 addition. Here hard nucleophile, that's why it is 1,2 addition. Then the next example, you have orthoamino benzoic acid reacting with iodine chloride. You should find what will be the final product. Here you have amine and acid. There are many possibilities including chemoselectivity and regioselectivity. Here you have two conditions, but our focus is regioselectivity. Here you have two possibilities. Amine or acid influence the incoming group because amine is the ortho para director Acid is the meta director. And chemoselectivity is iodine or chlorine reacts. Here chlorine reacts because of iodine easy removal. Here iodine reacts because of iodine is the most electropositive in nature. Chlorine eliminates, you have iodine attacks. But where the iodine attack? Ortho, meta, para. Here R will be the major product which is para to amino, meta to acid because it obey all the possibilities. Iodine reacts, meta to acid and para to amine there. The concept you have to learn here is you have to master not only the regioselectivity, chemoselectivity also because many problem comes with combination of both the selectivity. Then the next example, you have conjugated ketone which is quinone like architecture. You have methyl and methoxide heating it up and butadiene is there. You should find what will be the final product. Here you have two dienophile and diene. Definitely it's a Diels-Alder reaction which is 4 plus 2 cycloaddition. Where the regioselective come, which dienophile reacts or which diene A or B reacts. Dienophile by definition should be electron withdrawing group attached. Here electron density should be lesser. So if you look at it, electron density of methyl is lesser than O-methyl because O-methyl is mesomeric. So O-methyl don't react, only B reacts which gives major product. So the ring closer you have 4 plus 2 cycloaddition which is fusion reaction. B will be the major, A will be the minor product. The concept you have to learn here is regioselectivity promoted by the electron density of the dienophile. Then the next example, you have conjugated ketone which is cyclohexenone. You are reacting with dimethyl copper. You should find what will be the final product. Here the hard and soft nucleophile condition because you have conjugated ketone. Whenever you see conjugated ketone, you think of Michael addition possibility. Here copper nucleophiles are soft because of bigger size and the possibility of charge spreading. So CH3 nucleophile is soft in nature. Hard nucleophile undergo 1,2 addition. Soft nucleophile undergo 1,4 addition. Here nucleophile is hard so it attacks the fourth position and the bond migrates. You have 1,4 addition here. So regioselectivity promoted by the softness of the nucleophile. The concept you have to learn here is whenever you see conjugated ketone, you should apply regioselective addition which is called Michael addition. Then the next example, you have benzene attached with two different functional group which is amine and ketone. Basically it's amide group. Amide group, N-amide is there, carbonyl amide is there. The benzene attachment is different here. You are doing nitration with sulfuric acid and nitric acid. You should find what will be the final product. Basically, the attachment of functional group is different, which promote the regioselectivity. This is the best example of regioselectivity by the reagent because nitrogen has lone pair, it promote the electron. It direct the incoming group to ortho and para position. On the contrary, carbonyl group is sp2 hybridized, it's electron withdrawing in nature. It direct the incoming group to meta. So, if the amine attachment is there, substitution happen at para. Ortho has little steric effect, so only para is the major product. And if carbonyl is attached, carbonyl is electron withdrawing group. It promotes the meta substitution of the nitro group. The concept you have to learn here is regioselectivity can promoted by the reactant. Here electron density dictated by the reactant electron density. Then the next example, you have cyclohexane with conjugated ketone and isolated alkene and methyl groups. You are reacting with sulfur ierate which is dimethyl substituted, sulfur methylene with charges. You should find what will be the final product. Here you have three possibilities A, B, C. But here nucleophilic attack is the major one. Since you have conjugated ketone, as we discussed already, 1,2 addition and 1,4 addition, sulfur halides are harder, so 1,2 positivity is the major one. Even though it has 3 pi bonds in the system, only conjugated ketone will be attacked because of the 1,2 addition. So reaction happen at the second carbon, not with any other alkene. It attacks. Finally, methylation happen at the carbonyl. The concept you have to learn here is sulfur halides are hard. It will undergo 1,2 addition. Then the next example, you have conjugated ketone. Ketone and alkene is there. You have two methyl groups at the terminal. You are reacting with two different reagents, alkyl lithium and thiol. You should find what will be the final product. Here two different reagents you are using. Reagent controlled regioselectivity. Basically we already seen if you look at the conjugated ketone, you should analyze the Michael addition possibility. Soft nucleophile mean it promote 1,4 addition. Hard nucleophile mean it promote 1,2 addition. Alkyl lithium promote the harder nucleophile like Grignard reagent. So 1,2 addition happen. On the contrary, thiols are soft nucleophile. Why? Because it's bigger and polarizable. So charge will be spread, it will become soft. So soft nucleophile undergo 1,4 addition. So the attack happen at 4 O minus forms. Finally, hetoenol tautomerism occur. You have 1,4 product. The concept you have to learn here is sulfur nucleophiles are soft. It will undergo 1,4 addition. Alkyl lithium nucleophiles are hard. It will undergo 1,2 addition. Then the next example, you have naphthalene with amide attachment and two methyl groups. You are reacting with bromine and ferric chloride. You should find what will be the final product. Here two rings are there where the reaction happening is the real question, that is called regioselectivity. Since you are using ferric chloride is the Lewis acid, it promotes the ring. So both ring will be activated. Which rings reacts is the regioselectivity. Here A ring will be electron denser because of amine electron donating ability. So bromine attacks A. Again the question comes, incoming group will undergo meta or para because methyl group also there. Amine is mesomeric in nature because of lone pair very strong, it dominates. So only para to amine will form. So two regioselectivity, one is ring regioselectivity, another is para regioselectivity here. The concept you have to learn here is regioselectivity can be promoted by the mesomeric effect as well as the ring electron density. Then the next example, you have benzoic acid. Ortho position you have benzyl attachment reacting with SOCl2, aluminum chloride, zinc amalgam and HCl. You should find what will be the final product. Here regioselectivity come by ring closure. How the ring will be closing is the major question here. First step you are using SOCl2 which is the chlorinating agent. So OH becomes Cl there. So Fidelkraft's acylation is possible. But how the ring will close? Ring can open at any size because you have ortho and para substitution possible. Para will create the strainful ring, only ortho create the major product because 6-member rings are stable and zero strain. So the ring closure happen at ortho position which is 6-member ring. Then Clemmensen relation happen. You have final product. The concept you outlined here is regioselectivity can promoted by the ring size. Here 6-member ring is stable which in turn promote the regioselectivity. Then the next example, you have naphthalene, side chain you have ester, you are using aluminum chloride and acid hydrolysis. We should find what will be the final product. Here basically price rearrangement occur. Here you are using ester and aluminum chloride, which is Lewis acid. So the possibility of price rearrangement CH3CO acyl group migrates. Here where it will migrate. Normally in naphthalene alpha and beta position only active. So the possibility is only at alpha or beta. Already beta position is occupied. The possibility will be A. That creates the regioselectivity. At the first step, as it attacks, you are creating the acyl cation. Acyl cation again attacks back. You have the final product which only occur at alpha, particularly in the B ring, not in the A ring. So the reaction is regioselective both in terms of ring as well as ortho position or alpha position. The concept you have to learn here is in naphthalene regioselectivity only occur in A or B, alpha or beta. Then the next example you have indole, N-methyl is there and trimethylsilyl also there. You are using vinyl cyanide and dichloromethane. You should find what will be the final product. The reaction is interesting because mesomeric nitrogen creates the nucleophile here. Nitrogen lone pair travel, which create the possibility of nucleophile, which will attack another starting material, which is cyanide. It attacks, you have the new CC bond. Finally, you have silyl elimination because trimethyl is a good leaving group. It eliminates, you have new final bond, which is only 3 substitution. Here, two kind of regioselectivity is achieved. The incoming group can attack A or B, but only B is possible because of mesomeric nitrogen. In the ring also, 3 positions are there, but only 3 is favorable because of the electron transfer create the possible nucleophile at the third position. The concept you have to learn here is mesomeric effect also can dominate the principles of regioselectivity. Then the next example, you have hydrazine which is attached with cyclohexyl ring, methyl lithium and ether you are using. You should find what will be the final product. The reaction is called Sapphiro elimination, one of the important reaction. First step will be abstraction of proton. There are many protons, but only removal of the selective proton leads to the final product. The reason can be anion stability because anion primary is stable, tertiary is unstable. So secondary anion form. The anion travels. N2 and tosylate are good leaving group, both leaves. You have finally alkene formation. Here regioselectivity happen at the first step, the removal of the hydrogen. So regioselectivity can be a part of large molecule synthesis or organic conversion. The concept you have to learn here is always stable intermediate form. Here primary anion form which promote the regioselectivity. Then the next example, the starting metal is quinoline which reacts with lithium and liquid ammonia. You should find what will be the final product. Here regioselectivity occur in the reduction process, basically a bitch reduction. Here quinoline provide two possibility, A or B ring can reduce. The reduction is called bridge reduction which will form 1,4-diene. So either 1,4-diene form at the A ring or B ring. Here B ring is favorable. Why? Because reduction is basically a donation of electron. Nitrogen makes the ring electron deficient because of its electronegativity. So electron deficient ring pull the electron better. Reduction happen at nitrogen, not at the benzene ring. So in indole, nitrogen ring get reduced, which is pyridine ring get reduced, not the benzene ring. The concept you have to learn here is in quinoline, pyridine ring will get reduced quickly because of electron deficiency. Then the next example, you have benzene, side chain you have alkene, alkyne, the large moiety, and you are reacting with H plus. You should find what will be the final product. Here basically you are adding H plus. This is a kind of Wagner-Mervin situation because you can form two set of cation. Here regioselectivity at the first step occur. The stability of cation will be tertiary, secondary and primary. Secondary cation forms where cation is there. So the ring closure can happen because the possibility of Fiedel-Crafts alkylation happen. So ring close, you have the final product. You may wonder why the ring close at 5-member ring, not the 6-member ring, because ring rigidity don't allow the situation. So only adjacent ring closure happen. So two stereoselectivity, one is from cation stability, another is from ring size. The concept to outline here is many factors can control the regioselectivity. Here cation stability and the ring size control the reaction. Then the next example, you have cyclohexene which is attached with tetrahydropyrrole and you have conjugated ketone. You are doing acid hydrolysis. You should find what will be the final product. The reaction will be enamine reaction. First step will be mesomeric nitrogen create the nucleophile. The nucleophile is carbon nucleophile which is soft, so it only attack 1,4 position because it is a Michael addition reaction. So new CC bond forms. Finally hydrolysis remove the imine there. You have ketone. Here regioselectivity happen due to the nucleophile. Since the nucleophile is soft, only 1,4 position addition happen. Then the next example, you have cyclohexane with exocyclic double bond and you have ketone. You are reacting with hydrogen cyanide and potassium cyanide. You should find what will be the final product. Here cyanide is the soft nucleophile, so it will go 1,4 addition which promote the regioselectivity. Actually you should know the fact that cyanide is the soft nucleophile which promote the regioselectivity. Here you have alpha beta and saturated ketone, so 1,4 and 1,2 addition is possible. Since cyanide is soft, add in the fourth position. Then you have O minus, then O minus become OH. Then ketoenol tautomerism occur, you have the final product. So if you look at it, you have 1,4 addition as the final step. The concept you outline here is cyanide is the soft nucleophile which will promote the regioselectivity in 1,4 form. Then the next example, you have naphthalene and you have ketone. It is attached with triphenyl group. You are using acidic condition. You should find what will be the final product. Here you have ketone, you are using acid. Acid activates the carbonyl, you have cation. Then the cation can switch to the phenyl group because phenyl group can stabilize the cation better. So the cation migrates, you have the possibility of Fiedel-Crafts acylation reaction. Since the cation is strong, it can act as a electrophile. It attacks the benzene ring, you have the final product. Here where the regioselectivity comes, regioselectivity come in the attack of the cation because it can attack anywhere, but it will only attack in the alpha position to reduce the ring strain. So regioselectivity achieved by 5-member ring formation. The concept we outline here is in the long chain compound regioselectivity dominates to promote the lesser ring size. Then the next example, you have the acid which has 1,2,3 phenyl group. You are reacting with hydrogen fluoride. You should find what will be the final product. Here the problem in the blind side, you have to redraw the phenyl group at terminal because it gives the possibility of Fiedel-Crafts acylation. So you are creating the acid. So your acid and phenyl ring closure is possible. So first step OH removal will be there because HF is the strong acid, it pull the OH from the system. So the acyl cation formation happen. Acyl cation can attack the benzene ring, but it is promoted by two factors because 6-member ring is stable and methylene group is the ortho para director. So only possibility is the second position because which will obey both the condition. So final product is 6-member product. The concept you outline here is the regioselectivity strengthened by many factors. Here ring stability as well as methylene group ortho directing ability. Then the next example, you have cyclohexene attached with acid and methyl group. Both are stereochemically specified. You are using iodine and sodium hydroxide. You should find what will be the final product. Here the problem is in the 3 dimension. So we have to redraw the molecule for the 3 dimension. So cyclohexene chair form we written. Acid you are using the iodine. Iodine is the bulky molecule, so it is attacked from below. Then you have acid. Acid can open the iodine ring. It is like strainful cyclopropane. So ring has to open. Ring can attack either 7 or 6, but only 7 is possible because of ring rigidity. For 6, the bond has to stretch more, so attack happen only on 7. That is the regioselectivity here. After you redraw, you have the final molecule. The concept you have to learn here is always you think for the possibility and imagine the reaction. According to that, you have to redraw the molecule to get the better regioselectivity. Then the next example, you have cyclopentene, acid and alkene. You are using sodium bicarbonate and iodine. You should find what will be the final product. Here first step you are using the base. Base remove the proton. You have the anion. Anion is the nucleophile. So it's ready for the attack. Then you are using the iodine. Iodine can attack either alkene which is on the ring and which is on the side chain. Side chain is very interesting because side chain always rotates a free molecule. So iodination is not effective. Even though iodination happen, it is minor. The major will be ring alkene substitution. Then O minus attack. O minus attack also regioselective. It will only attack on A, not B because of regioselectivity. Why regioselective? The nucleophile cannot stretch its carbon bond to attack the B. So A is the major product. Here you achieve 2 regioselectivity. Among the alkene you choose one. Among the 2 iodine carbon you choose the one. The concept you have to learn here is iodinium ion ring opening always involve regioselectivity. Then the next example, you have cyclohexanone. Second position, you have methyl group. You are reacting with methyl diamine, butyl lithium and ethyl bromide. You should find what will be the final product. The reaction basically a stock enamine reaction. Ketone become imine there. After becoming imine, alpha hydrogen become acidic. So butyl lithium can promote the nucleophile formation. So anion become nucleophile there. Anion attacks the methyl. You have final new CC bond. Further hydrolysis leads to the ketone there. Basically you are doing alpha substitution. Where is the regioselectivity? Since the carbon has many hydrogen, only one is absorbed because of the regioselectivity. One is steric, one is less steric. Steric free carbon is alkylated because SN2 reaction required backside attack. Steric free carbon is good for SN2 reaction. So regioselectivity achieved through the steric effect. The concept you have to learn here is in stock enamine reaction, always less hindered anion formed which will act as a nucleophile. Then the next example, you have toluene, meta position you have bromine and long chain with amine. You are using phenyl lithium. You should find what will be the final product. You are using phenyl lithium. You should find what will be the final product. Here you have halogen. You are using the butyl lithium. So benzyne formation is dominant here. First step will be anion and bromine removal form the benzyne. Then you have amine and benzyne. Benzene is highly unreactive. It should open. So benzene can be attacked two way, A type and B type. A type attack leads to the 7-member ring. B type attack leads to the 6-member ring. But 6-member ring is more stable than 7-member ring. which gives the regioselectivity here. The concept you have to learn here is ring closure always achieved with regioselectivity with less ring strain. Then the next example, you have cyclopentadiene with exocyclic double bond, which is isopropyl in nature. You are reacting with methyl lithium. You should find what will be the final product. Here methyl lithium can attack many carbon A, B, C, D, but only attack on the A carbon leads to the stable compound. Let us analyze the other possibility. B attack leads to the unstable tertiary anion. C attack leads to the secondary anion. D attack also secondary anion. But A attack leads to the aromatic anion, which is 4n plus 2. N is 1 here, 6 pi electron. So it's a pseudo aromatic stable compound. So CH3 attack dominated here by anion stability. So regioselectivity achieved through the aromaticity. Then the next example, you have benzene, ether and methyl on the side chain. You are reacting with butyl lithium, carbon dioxide, acidic hydrolysis. You should find what will be the final product. The reaction involved regioselectivity. Why? Because you are using the butyl lithium. Butyl lithium promotes ortholithiation. What is ortholithiation? Ortho hydrogen can be activated through lithium because the intermediate is very stable. Here, lithium stabilizes the 6-member state as well as removal of H. It forms nucleophile there. It will be like Regnard reagent. Only ortho position you generate the nucleophile. Then CO2 attacks, you have acid formation. There are the many possibility, but only one side ortho is achieved because of lithium coordination. The concept you have to learn here is ortholithiation is a regioselective reaction. Only ortho hydrogen will be removed. Then the next example, you have cyclohexanone. Third position you have O-methyl. You are reacting with phenyl magnesium bromide in acidic condition. You should find what will be the final product. Here you have conjugated ketone. So chances of Michael addition is there. But phenyl magnesium bromide gives phenyl as the hard nucleophile. Hard nucleophile only involve 1,2 addition. This is the regioselectivity by reagent. So pH minus attacks the ketone, not the alkene. So pH attacks, you have alcohol formation. Further, you are using the acidic condition, which leads to the conjugated ketone. The concept you have to learn here is whenever you see conjugated ketone, you always imagine regioselectivity through Michael reaction. Then the next example, you have cyclic ether with oxygen and sulfur reacting with sodium hydroxide and reacting with bromochloroethylene. You should find what will be the final product. Here base you are using, base subtract the proton, but which proton will be removed? You can remove both proton, but second proton removal only leads to the stable anion because anion stabilized by sulfur back bonding. So the structure A is stable with the anion. Then the anion attacks. Which carbon it will attack? Bromine carbon or chlorine carbon? Bromine carbon will be attacked because bromine is a good leaving group when compared to chlorine. So it forms new CC bond. Here you achieve two regioselectivity. One is by hydrogen removal, another is by leaving group ability of the bromine. Then the next example, you have linear chain alkene with alcohol. Two methyl groups are there in the linear chain. You are reacting with iodine and sodium bicarbonate. You should find what will be the final product. Here alcohol and alkene is there. You are using the iodine. Iodine form iodinium ion. hydrogen ion is strainful. So how the ring will be open is the critical question here. It can open on either side. It open in such a way that it will create stable secondary cation, not the primary cation. So secondary cation form. It will attack by O, it form 5-member ring. Here regioselectivity is dictated by the cation stability. It involves the long synthetic process. So regioselectivity can be a part of large molecule synthesis, very important to decide the final product. The concept we outlined here is in this system, regioselectivity achieved through the cation stability. Then the next example, here you have epoxide with 2 methyl group, methanol in acidic condition you are using. You should find what will be the final product. Here acid you are using, acid attacks the O, it form OH there, it will form cation with oxygen. So ring is very strainful, it has to open. How it will open? As we seen already, two possibility of ring cation, A or B opening. B breaking leads to the primary cation, A breaking leads to the tertiary cation. So regioselectivity achieved through the cation stability. Then methanol attacks, you have the final product. The concept you outlined here is whenever you imagine epoxide in acidic condition, always think of regioselective ring opening. Then the next example, you have benzene attached with 2 methyl group reacting with lithium and liquid ammonia. You should find what will be the final product. By looking at lithium and liquid ammonia, you might realize it's a bichdation. Bichdation always happen away from electron donating group because intermediate is the anion. So there are two possibilities A and B. A is the major product because anion form away and reduced away from electron donating methyl group. In bichdation, so the fact here is in bichdation double bond form near the alkene, that is the fundamental mechanistic pathway. So the concept we outlined here is regioselectivity in bichdation occur through the stability of anion. Then the next example, you have epoxide attached with 2 methyl group. You are reacting with sodium methoxide. You should find what will be the final product. Here methoxide you are using. Epoxide is a strainful ring. So the ring tried to open itself. So it is a SN2 mechanism. Methoxide can attack A or B pathway. A pathway is very steric. So SN2 mechanism is not possible. So only B is the major pathway. So O minus is there. Then O minus become alcohol by protonation. Here regioselectivity comes from the fact that where the ring will open, A pathway or B pathway. B pathway is the right answer because of its mechanism. Then the next example, epoxide you have with 2 methyl group and the two different condition, two different reagent, acidic condition with methanol, basic condition with sodium methoxide. So two different condition, you should find what will be the final product. Here two different pathways, two different mechanisms. Acidic condition followed the P pathway. Acidic condition involve cation formation. So the stable cation form. So the ring is open on dimethyl side. On the contrary, methoxide is followed through SN2 mechanism. SN2 mechanism required backside attack which should be steric free. Here A is steric, B is less steric. So attack happen on the B side. Ring open on the opposite then P pathway. So final product is the alcohol which is different from the acid condition. The concept we outlined here is two different reagents, two different regioselectivity. So reagents can control the regioselective pathway. Then the next example, you have dibromocyclohexane. You are using alcoholic KOH. You should find what will be the final product. Alcoholic KOH remove the HBr, which is dehydrohalogenation. Here many hydrogen removal is possible, but you have to remove the two halogen. So only pathway is A hydrogen removal. Other pathways leads to the alkyl bromide. sp2 carbon will form. Difficult to remove the second bromine. If you remove the hydrogen from same system, you have benzyne kind of architecture. You have cyclohexane. It is impossible to stay with cyclohexane because of sp2 carbon. So only removal possibility is A. A remove, you have alkene. Again, next hydrogen remove, you have conjugated diene there. Here conjugation promote the regioselectivity as well as favorable hybridization promote the final product. The concept you have to learn here is whenever you do dehydrohalogenation, look for the conjugation and achieve the maximum stability. Then the next example, you have cyclohexane with alcohol, many methyl groups. You are using NOCl, light and HCl. You should find what will be the final product. The reaction is naming reaction, Barton reaction, which is very selective to delta hydrogen. Here actually 4 delta hydrogen is there. Only one delta hydrogen, which is A, that will be removed, which give excellent regioselectivity because of positioning. The stereochemical is positioned better, so A hydrogen will involve in the transfer. You have ONO, then hydrogen transfer occur, then NO forms. Finally, you have ketone. First step is our interest because of regioselectivity. Barton reaction occur through perfect 6-member intermediate. Only A hydrogen give the best position. The concept you have to learn here is in cyclic system, Barton reaction involves regioselectivity. Then the next example, you have cyclic system with amide ester architecture with stereochemically specified isopropyl. You are reacting with LDA, benzyl bromide, lithium aluminum hydride. You should find what will be the final product. Here LDA you are using. LDA is the base, abstract the proton. So anion will form. Anion act as the nucleophile. Attack benzyl bromide. Attack from below. Then you have interesting position. Lithium aluminum hydride. Two carbonyl is there. Which carbonyl will be reduced? A carbonyl and B carbonyl. B carbonyl electrophilicity is reduced because of two electron donating atoms. Nitrogen and oxygen donate weaken the carbonyl. So only A is involved. Finally, you have removal of the ring. Final product is alcohol here. Here two carbonyl regioselectivity achieved in the one carbonyl through the electron donating ability of nitrogen and oxygen. P carbonyl has two donating groups, so it is weak. So A is reactive. Regioselectivity is achieved here. Then the next example, you have fused system, diketone and dialkene. You are heating it up with cyclobeta-diene. You should find what will be the final product. Here diene and dienophile situation. It is a Diels-Alder reaction, but two dienophile is there A and B, which will react. Dienophile means it should be electron deficient, so the alkene attached with carbonyl is very reactive, not the isolated one. So the alkene attached with carbonyl reacts. You have 4 plus 2 cycloaddition, and you have the final product. So regioselectivity in alkene here. The carbon deficiency of alkene decides the final product. Then the next example, you have cyclohexene with ketone, exocyclic alkene. You are reacting with sulfur halide and sulfoxide halide. You should find what will be the final product. The reaction is all about regioselectivity. Sulfur halide gives hard nucleophile. Sulfoxide halide gives soft nucleophile. Since you have conjugated ketone, 1,2 addition and 1,4 addition is possible. Hard nucleophile give 1,2 addition. Soft nucleophile give 1,4 addition. Sulfoxide nucleophile gives soft. So 1,4 addition happen. You have methylation at 3,4 carbon. On the contrary, sulfur nucleophile is hard. Attack in the second position. So methylation happen at second position. The concept you have to learn here is two different nucleophile based on the hardness. It attacks the 1,2 or 1,4 position, which in turn promoted the regioselectivity. Then the next example, you have benzene in side chain cyclopentane, ether at the side chain. We reacting with butyl lithium and methyl iodide. You should find what will be the final product. Here basically ortholithiation happen. It's a typical regioselective reaction. Even though the compound has ortho-meta para, only ortho position is lithiated. This is because specific stability of lithium intermediate due to the side chain oxygen lone pair, which will promote the 6-member intermediate with lithium. Lithium weaken the ortho hydrogen, so it forms nucleophile. It attacks. You have the final CC bond there. So the concept you have to learn here is whenever you have lone pair containing atom, you should imagine ortholithiation, which will promote regioselective orthoalkylation. Then the next example, you have benzene, you attach with 5-member oxygen and O-methyl group. You are reacting with sodium and ammonia, ethyl alcohol. You should find what will be the final product. Here basically the Bitch reduction reaction. Intermediate is diradical and dianion. So you should form dianion with the stability. Dianion cannot form at the connected carbon because of oxygen lone pair. So dianion only form at the benzene, which is in between ring and O-methyl middle carbon. So reduction happen at the middle carbon. So 1,4-diene is formed, the exclusion of middle carbon. The concept you have to learn here is in Bitch reduction, anion stability promote the regioselectivity. Then the next reaction, you have anisole fused with cyclohexanone. You are reacting with sodium and ammonia ethyl alcohol. You should find what will be the final product. Here you have Bitch reduction possibility. Already we know that anion stability dictates the regioselectivity here. We should find where the reduction happened. Since O-methyl is mesomeric electron donor, carbonyl is electron withdrawing, you can meaningfully guess the anion formation. So the diradical form ortho to O-methyl, ortho to carbonyl, which will form perfect 1,4 position. Dianion forms, reduction happen. The concept you have to learn here is in Bitch reduction, anion stability is important. Electron donating group promote the anion stability. Electron withdrawing group destabilize the anion. Both factors control the regioselectivity here. Then the next example, you have quinone, methyl and methoxide is there. You are heating it up and you are using cyclobutadiene. You are heating it up. You should find what will be the final product. Here diene and dienophile situation. Two alkenes are there. Which alkene reacts? One is with methyl, one is with methoxide. As you are aware, mesomeric effect of methoxide is stronger than the inductive effect of methyl, and the important fact is dienophile should be electron deficient. So only B is the possibility because B is electron deficient than A. So the Diels-Alder reaction happen in the B. So fusion happen. You have the final product. The concept you have to learn here is regioselectivity here promoted by the electron deficiency of the dienophile. Then the next example, you have naphthalene, sulfuric acid you are using 10 degree and 160 degree. You should find what will be the final product. Here you have alpha and beta substitution is possible. So we redraw with hydrogens there. You achieve regioselectivity through temperature. Low temperature is the steric product which is kinetic and less stable. High temperature only stable product survives. So beta substitution is there. So low temperature it's a kinetic product. High temperature it is a thermodynamic product. Here temperature completely control the regioselectivity. Low temperature promote alpha substitution. High temperature promote the beta substitution. Then the next example, you have aniline reacting with sulfuric acid at low temperature, sulfuric acid at high temperature. You should find how temperature influence the final product. Here at low temperature, just a salt formation. It is an acid-base reaction. You are having ammonium and sulfate salt, direct salt formation. On the contrary, high temperature leads to the sulfonation reaction. It's only possible at high temperature. Low temperature, simple acid-base reaction. High temperature, it's a para substitution. The concept you have to learn here is regioselectivity here controlled by the temperature. High temperature stable para product form. Low temperature kinetic acid base reaction occur. Then the next reaction you have cyclohexene which is alpha beta unsaturated ketone. You are reacting with methyl magnesium bromide and diethyl copper. We should find what will be the final product. Here you have two different reagents, methyl magnesium bromide and dimethyl copper. Basically it's a 1,2 and 1,4 addition situation. Soft nucleophile attacks 1,4 position. Hard nucleophile attacks 1,2 position. Here magnesium gives hard nucleophile, copper gives soft nucleophile. So methyl magnesium bromide attacks 1,2 position. Dimethyl copper attacks the 1,4 position. The concept you have to learn here is reagents also can control the regioselectivity. Here soft and hard nucleophile control the final addition product. Then the next example, you have conjugated diene with O-methyl group. You are reacting with electrophile. You should find what will be the final product. This is the classical example. E plus can attack 2 alkene. Which alkene is the final product? Which alkene is the regioselectivity? Here, cation stability dictate the final product. If E attacks the first alkene, it forms secondary cation. Don't have extra stability. But if it attacks the second alkene, which is B, it has extra stability because mesomeric effect on methoxide can donate the electron, stabilize the cation. So it has extra resonance structure, extra stability. So the regioselectivity achieved here through the cation stability with the help of mesomeric effect on methoxide. Then the next example, you have allyl chloride with sulfur with SH nucleophile in ethanol. You should find what will be the final product. Here you have alkene and you are attacking with nucleophile. So direct replacement and SN2 prime mechanism is possible. It's basically the competition between SN2 and SN2 prime. To identify the difference, I given the star here. If SH attacks the A position, you have star at terminal. If SH attacks the B position, you attack the label carbon. Both positions are technically same, but to create the difference, we label the product. So basically the regioselectivity through two different mechanisms, SN2 versus SN2 prime. Then the next example, you have conjugated ketone reacting with two different reagents, alkyl lithium and thiol. You should find what will be the final product. Here the regioselectivity by the reagent condition. It's like same hard and soft nucleophile problem. Alkyl lithium provide the hard nucleophile, thiol provide the soft nucleophile because sulfur is big, polarizable and soft. So soft nucleophile undergo 1,4 addition, hard nucleophile undergo 1,2 addition. Since alkyl lithium provide hard, alkyl group attacks the second position, you have the final product. Then the thiol is the nucleophile. Thiol attacks the fourth position, which is Michael addition. So 1,4 addition happened. Then the enol tautomerism occur. You have the final product. Here regioselectivity achieved through the reagent. Reagent can give hard nucleophile and soft nucleophile, which promote the regioselectivity here. Then the next example, you have indole reacting with the electrophile. You should find what will be the final product. Electrophile can attack many carbons here, including nitrogen, but only attack happen on the B ring in third position. The reason is based on mechanism. Only attack on the third position give many resonance structure. So attack happen on the third position. It will not attack the A ring. Why? Because here 6 electron in 5 atoms. So B is electron richer. So reaction happen at B here. So the final product is 3 substituted product. The concept you have learned here is in indole, third position is regioselective. Finally, electrophile attacks the third position. Then the next example, you have benzene with two methyl group reacting with bromine in light, bromine in acidic condition. You should find what will be the final product. This is the reagent control regioselectivity. Bromine in light promote the radical mechanism. Bromine in acid promote the ionic ring substitution mechanism. Radicals are stable at the benzylic position. So bromine form at the benzyl position in the light condition. On the contrary, bromine attacks the ring in terms of Lewis acid. Because Lewis acid activate the benzene ring, substitution happen at the benzene ring. So two different reagent, two different product, typical reagent control regioselectivity. Then the next example, you have diketone with methyl group which is in the cyclohexane. You are reacting with alpha beta unsaturated ketone with butyl lithium. You should find what will be the final product. Here butyl lithium you are using. Butyl lithium can abstract the proton. The proton creates the carbon nucleophile. Carbon nucleophiles are soft, which will have 1,4 Michael addition with the conjugated ketone. Here nucleophile forms which attacks the fourth position. Then intra-aldol condensation happen. Then again the butyl lithium abstraction. Two hydrogens are possible, but only one hydrogen abstracted because primary anion is stable. Finally, aldol condensation happen here. Here two regioselectivity. One is Michael addition, second is proton abstraction. The concept you outline here is Michael addition is inevitable in terms of regioselectivity. Then the next example, you have cyclohexanone. First position you have alkyl group. You are reacting with alpha, beta unsaturated ketone with butyl lithium. You should find what will be the final product. Here first position is proton abstraction which form carbon nucleophile. Carbon nucleophiles are soft. It always attacks the 1,4 position which is the Michael addition reaction, highly regioselective. Only fourth position is favorable. So 1,4 addition happen. Again diketone condition with basic condition. Proton abstraction happen. Only terminal proton is abstracted because to create stable primary anion which in turn promote the aldol reaction. Here two regioselectivity, one is Michael addition, another is proton abstraction. Then the next example, you have alpha naphthol, alcohol with naphthalene, lithium and liquid ammonia. You should find what will be the final product. Here you are having bitch reduction condition. Where the reduction happen is the real question. Reduction is basically a electron donation. So electron deficient ring get reduced first. Here oxygen contain lone pair which is mesomeric. Donate the electron to the ring, make it electron richer. So ring is electron deficient than A. So A ring is deficient than B. So the reduction happen at the A. So 1,4 reduction happen. You have the final product. The concept you outline here is reduction happen quickly at the electron deficient ring. So the regioselectivity dictated here by the electron deficiency. Then the next example, you have methyl cyclohexenone reacting with dimethyl copper, methyl magnesium chloride and allyl chloride. You should find what will be the final product. Here you are having Michael addition condition because conjugated ketone and nucleophile. Copper makes the nucleophile soft, so 1,4 addition is possible. So methyl adds to the fourth position. You are generating the nucleophile. Nucleophile attacks the chlorine. You have new CC bond. The concept you outline here is when you mix the copper reagent with methyl magnesium chloride, the nucleophile becomes soft, which promote the regioselectivity. This is the best example of regioselectivity controlled by the reagent. Then the next example, you have cyclohexene with side chain amine and you have conjugated ketone. You are doing acidic hydrolysis. You should find what will be the final product. Here you have imine condition. Imine generate the nucleophile. Carbon nucleophiles are soft. You are reacting with conjugated ketone. So 1,4 Michael addition is possible. Nucleophile attacks the fourth position. You have new CC bond. The concept you outline here is imine generate the carbon nucleophile which is soft, which in turn promote the Michael addition and the regioselectivity. Then the next example, you have anisole fused with 5-member oxygen. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here you have bitch reduction condition, benzene with sodium and ammonia. Basically diradical forms. The diradical convert into anion. The anion has to be stable. Anion cannot form near the lone pair because of repulsion. So it form in the benzene ring, not the connected carbon. Anion form, it reduce. So the concept you outline here is bitch reduction completely controlled by the stability of anion, which promote the regioselectivity. Then the next example, you have conjugated ketone and you have organometallic compound, lithium and copper with cyanide and trimethylsilyl chloride. You should find what will be the final product. Here, whenever you come with copper, you always think of soft nucleophile. Soft nucleophile promote the regioselectivity in the fourth position. Basically, it's a Michael addition. So the reagent donate vinyl there. Vinyl is the nucleophile. It attacks the fourth position. Trimethylsilyl chloride stabilize the enol form. So O-silyl bond forms. So finally, you have substitution at the fourth position. The concept you outline here is copper always provides soft nucleophile which promote regioselective 1,4 Michael addition. Then the next example, it is a classical example, toluene and nitrobenzene reacts with electrophile. You should find what will be the final product. Here electrophile is there. In methyl substitution, ortho and para is stable because of electron density. On the contrary, nitro, electron withdrawing group, only meta is the electron denser position. So electrophile attacks meta. So regioselectivity achieved by the reactant here. If you are interested, study mechanism separately. So electron withdrawing group promote the meta substitution. Electron donating group promote the ortho and para substitution. So regioselectivity promoted by the reactant here. Then the next example, here you have cyclohexenone, which is alpha beta unsaturated compound. You are reacting with sulfoxide halide. You have to find what will be the final product. By looking at the sulfoxide halide, you might realize it's a Korey-Chakowsky reaction. Basically, it's a 1,4 Michael addition. Why? Because sulfur nucleophiles are soft, so it attacks the fourth position. You have new carbon-carbon bond. Then alkene becomes cyclopropane because of leaving group ability of dimethyl sulfoxide. Finally, end up with methylation at alkene. Here regioselectivity achieved in the first step because halide is soft nucleophile attacks the fourth position. You have the final product. The concept you have to learn here is sulfoxide halide is the soft nucleophile. Then the next example, we are comparing the sulfur halide. You have conjugated cyclohexenone reacting with sulfur halide and sulfoxy halide. You should find what will be the final product. Here as we seen already, sulfoxide halides are soft, sulfur halides are hard. So hard nucleophile undergo 1,2 addition, soft nucleophile undergo 1,4 addition. So sulfur halide attacks the second position, which is 1,2 addition. You have methylation happen at the carbonyl. On the contrary, sulfoxide halides are soft. It attacks the fourth position. You have methylation happen at the alkene there, which is 3,4 alkene. So two different reagent, two different regioselectivity. The concept you have to learn here is sulfur nucleophiles are hard, sulfoxide nucleophiles are soft. Then the next example, you have conjugated ketone reacting with hydrogen cyanide and potassium cyanide. You should find what will be the final product. Here you are having conjugated ketone and a nucleophile. So where the reaction happen is by nucleophilicity of the cyanide. Cyanide is the soft nucleophile. Soft nucleophile undergo 1,4 addition. Hard nucleophile undergo 1,2 addition. Since cyanide is the soft nucleophile, it will undergo 1,4 addition. So cyanide attacks the fourth carbon. Charge travel to oxygen. Then protonation. Finally hetoenol tautomerism. You have the final product. The concept you have to learn here is cyanide nucleophiles are soft. It will undergo 1,4 addition. Then the next example, you have cyclic compound which is alpha, beta unsaturated ketone and you have isolated alkene. You are reacting with sulfur halide and sulfoxy halide. You should find what difference it can make in the product. Basically, the regioselectivity by reagent here. Here, sulfoxy halides are soft nucleophiles. Sulfur halides are hard nucleophile. Soft nucleophile undergo 1,4 addition, which is Michael addition. Hard nucleophile undergo 1,2 addition. Pure regioselectivity. Sulfoxy halide attack 3,4 position. So methylation happen at the 3,4 position. So cyclopropane ring form at the 3,4 position. On the contrary, sulfur halides attacks the carbonyl. You have methylation at the carbonyl group. So finally, you have methylation at carbonyl, methylation at 3,4 alkene. Here, isolated alkene not at all touched here. So the concept you have to learn here is sulfur halides are hard, sulfoxide halides are soft. Then the next example, here you have cyclohexenone alpha, beta unsaturated ketone. In the first set of reaction, you are reacting with sodium borohydride with methanol. Second reaction, sodium borohydride with cerium chloride. You should find what will be the final product. The reaction is a regioselective reduction. If you use simple sodium borohydride, it will undergo 1,4 addition. Since the hydrogen nucleophiles are soft, it attacks the fourth position. So 1,4 addition happened, which is the Michael addition reaction. On the contrary, if you use cerium chloride can activate the carnel. It promote the 1,2 addition. So cerium promote 1,2 addition. Without the cerium, Michael addition happen. The concept you have to learn here is you can control the regioselectivity by the choice of the reagents. Then the next example, you have cyclopentadiene system. The heteroatom can be oxygen, sulfur or nitrogen. You are attacking with electrophile. You should find what will be the final product. Here all the heteroatoms are same, so reaction will be same. E plus attacks the second position, which will give major product. Even though all four positions are possible, E will be the major. The reason is resonance structure. If E attacks, cation travels, it has resonance stability both by delocalization of bibond and mesomeric lone pair of oxygen, sulfur and nitrogen. So all three will give same product, regioselective second position. The concept you have to learn here is heterocyclic ring with 5-member atom. Always choose the second position electrophilic substitution reaction. Then the next example, you have cyclobutene reacting with N-bromosuccinimide and hydrogen peroxide. You should find what will be the final product. Here you are using N-bromosuccinimide and hydrogen peroxide, which promote radical mechanism. In radical, allyl radical is stable. So allyl radical is more stable. Allylic bromination happen. Even though it has the 3 hydrogen removal possibility, only allylic hydrogen remove because of allylic radical stability. The concept you outline here is N-bromosuccinimide in the allylic condition promote the regioselective alpha bromination. Then the next example, you have cyclohexene. Side chain you have alkene and methyl group. You are reacting with metaperchlorobenzoic acid. You should find what will be the final product. The starting metal contains 2 alkene. You are using metaperchlorobenzoic acid. It's a kind of electron deficient compound, but it is the epoxidation compound. So it will only attack the electron rich alkene. So among the 2 alkene, methyl substitute is more electron denser because of electron donating ability of methyl group. So epoxidation happened with the A-methyl group. So A-methylation is the major, even though P has the possibility. Electron rich ring forms the final product. Here regioselectivity among the 2 alkene, electron rich alkene get epoxide. The concept he outlined here is metaperchlorobenzoic acid is electron deficient. Always attack the electron deficient alkene. Then the next example, you have quinoline. You are attacking with electrophile. We should find what will be the final product. Here electrophile can attack A and B ring. It also attack any position on the A ring. So 2 regioselectivity is possible. It will not attack B ring because of electronegative nitrogen. So only A is possible. In the A also it attacks only 5 and 8 because of electronic reasons. If you are interested, go and study separately. You can simply memorize this position. Both positions are meta to nitrogen. So the concept you have to learn here is quinoline will undergo substitution at 5th and 8th position. Then the next example, you have benzene with methoxide and methyl. You reacting with lithium and liquid ammonia. You should find what will be the final product. Here lithium and liquid ammonia mean bridge reduction. It's a 1,4 double bond regioselective reduction. Where the reduction happen? Since the intermediate is anion, it always away from electron donating group. You have many possibilities A, B, C. Among that A is major because B shows reduction near O methyl, C shows reduction near methyl. So only A is away from both methyl and methoxide. So the final product is A there. The concept you have to learn here is pitch reduction is the regioselective reduction. Always reduction happen away from the electron donating groups. Then the next example, you have chlorobenzene reacting with butyl lithium and anthracene. You should find what will be the final product. Here you have butyl lithium. It promotes the formation of benzyne through HCl elimination. Then benzyne is the nucleophile. Then benzyne can undergo 4 plus 2 cycloaddition, but it can attack any ring in anthracene A, B, C, but only B ring is weaker because of annihilation effect. There where regioselectivity comes, only B is reactive than A and C. Why B is reactive? Because only B reaction preserves the aromaticity, other reaction destroy the aromaticity. So the reduction happen at the middle ring without disturbing the stability by aromaticity. So the final product is B substituted product. The concept you have to learn here is regioselectivity in anthracene achieved through annihilation effect. Then the next example, you have cyclohexadiene with two exocyclic double bond reacting with phenyl chloride. You are heating it up. You should find what will be the final product. By looking at diene and dienophile, you might realize the Diels-Alder reaction, which is 4 plus 2 cycloaddition. But here two dienes are there. Which diene will react? Always diene reacts to create the stability. Here A diene reacts mean you have aromaticity. B diene reacts mean very strainful rigid carbon. Why strainful? It's a sp2 hybridization need 120 degree. So A is the major product because of created aromaticity. The concept you have to learn here is aromaticity is the controlling factor which promote the strong regioselectivity in Diels-Alder reaction. Then the next example, you have anthracene and maleic anhydride. You are heating it up. You should find what will be the final product. Here we seen already B ring in the anthracene is weak because of annihilation effect. So dihydride is the dienophile. Anthracene can act as a diene, only B ring. It attacks, you have 4 plus 2 cycloaddition Diels-Alder product. The concept you have to learn here is regioselectivity promoted by annihilation effect, which promote only B ring activation in the anthracene. Then the next example, anthracene with the substitution in the side chain alcohol. You are reacting with ethylene. You should find where the reaction center A, B or C because all are diene. You should find which will be the major product. Here you have 3 diene, 1 dienophile. Which diene reacts? As we seen already, middle ring is weak because of annihilation effect. Annihilation effect means partial aromaticity here. So B ring is very weak. B ring forms major product. A and C preserve the aromaticity. Only B ring forms the aromatic compound. So the concept you have to learn here is in anthracene B ring is weak. It will undergo Diels-Alder reaction, which in turn promote the regioselectivity.